Right.
Okay, perfect.
Right, so I'm going to talk about the evolution of MU69 from a binary planetesimal into contact via Kozai-Lidov oscillations and nebular drag. And if that sounds like a big title, it's because it is the title of the article. The article was submitted not long ago to the archive, you can see there. So I'm going to show first and explain it later. So this is the main result. So if you sleep during the talk, you already have here the main result. So in the left axis, you're seeing the semi-major axis against time. So these are 4 different models. The green and the blue one are kind of the same line. You barely see the difference between them. The green one has no dissipation at all. So this is the evolution of a binary. Green is just gravity. On the blue, you use also the tides of the 2 bodies. These tides can exert tides on each other. The yellow line is when things start, the orange line is when things start to deviate a little bit. You included now the quadrupole, the permanent J2 quadrupole of the bodies. And the red one is very different because then we include the drag. And as you include the drag, the system loses energy and the semi-major axis starts to decline. As you see on a low time scale, like millions of years, but still has an effect. On the middle plot is the mutual inclination of the bodies. You see the blue line, you would have some cycles that are regular. The period of the cycles is very short, so you barely see them. You just see a continuous blue line, but inclination varies very regularly. That's Kozai-Lidov oscillations. What you see is that when you include the quadrupole, the orange line, the oscillations start to become very chaotic. And on the left, on the right-hand plot, the last plot here, you see what happens once you include the drag. What is going on is that on top of these chaotic oscillations, the semi-major axis is also declining. So you see this line here is starting to go down, and then eventually the system reaches contact, which here happens in about 2 million years. So in a little bit more detail, I applied this model here to MU69. So MU69, you may remember from the flyby, is an object in the Kuiper belt. Altogether has about 30 kilometers, but it's formed of 2 lobes. And what is interesting about it is that, well, one of the many things that is interesting about it is that it's a member of the called classical Kuiper belt population, which means that these red objects here, the inclination is very low. Their eccentricities are usually very low too. So they are our best bets for pristine planetesimals, objects that were formed where they are and were not disturbed in the 4 billion years of the history of the solar system. So studying that means that we are looking at how a planetesimal looks like, probably the less processed objects. So this is a cartoon image here of how the formation of these objects and the evolution might have happened. So you have here basically the formation by streaming instability, and then you form these 2 lobes, and then something happens and that brings them into contact. And this is where I would like to focus on. So beyond the cartoon image, basically, how do you pass from a pebble disk to a formed object like MU69? So the first part, I'm not going to talk much about it, but that's most likely due to streaming instability. That's a model here calculated by Ruxin Li, published recently by David Nesvorny and collaborators, include I think Jake Simon also, who's here. What you're seeing here is that this model can reproduce the prograde and the retrograde distribution of binaries in the Kuiper belt. You're having here in solid line is the streaming instability model. The dashed line is the actual distribution of Kuiper belt objects. You see you have about 80% of binaries being prograde, 20% being retrograde, and the model reproduces that distribution. If is the only method that can reproduce that is not known, but the streaming instability seems to reproduce that. So I'm going to take that as the way that they form, and then I'll start from the bodies already formed, the two lobes, and calculate then the evolution of these two lobes and see how you can reach contact. So the main question here is then how the angular momentum was lost, right? So you have that they were in a mutual orbit. That means that they're not captured, which you can know because the alignment of the spin axis, right, it is very good. I mean, the two bodies have their axes aligned, both the minor and the major axis. And the colors are also similar, which implies they have a similar composition. They were not formed in independent orbits around the sun. And also, due to the lack of cratering and major faults, you can imply a slow merger, given also the strength that you expect for these bodies. The reference here says McKinnon 2020, but there is a recent article also by Julian Marhonik. That's actually where this SPH calculation was done, showing that you can only reproduce the shape with the lack of major faults here if the speed is very slow in the merger, like less than 5 meters per second. Already 10 meters per second cannot reproduce that. Another line of evidence for formation while gas is present, I mean, a quick formation, as you would expect from streaming instability, is the fact that the surface ices are very different than the surface ices that you see on bigger objects like Pluto. So on MU69, you see clear signs here of CH3OH, some tentative detection of water ice and HCN. But these ices here are different than the ices. They are clearly seen in Pluto, which are methane, molecular nitrogen, and carbon monoxide, which are clear here on Sputnik Planitia. So the question is, if you think that you form Pluto out of bodies like MU69, how do you reconciliate the fact that their chemistry looks different, right? You have in one body a different kind of ices that you see on the other one. So one of the best explanations for that is the fact that you can maintain these hyper volatiles only if the temperature is much lower than what their equilibrium temperature is now. Pluto and MU69 are of course quite cold, right? The temperature is 42 Kelvin, which is about here. But to maintain these ices, you need even lower temperatures than that. So to the left side of this plot here is when you lose the volatiles, and to the right hand side of this plot here is where you keep them. So big objects like Pluto, Triton, and others, they can keep these hypervolatiles because they're massive, but a small body like MU69 would only maintain them if the temperature is lower, like here, like 20 Kelvin or less. So what's going on is that in this side here, you have that these objects are being flambé, right, to the light from the sun. So what you need to retain these objects in MU69 is if they formed while the gas was there. So they're formed in an optically thick midplane that keeps the temperatures low. This is seen here in this plot here by KozaiLidov. So this is a very busy plot, but the way that you read that is here. On the right hand side, you have, on the bottom axis, you have the temperature. And on the y-axis here, you have the flux in number of molecules per area per time of the different species. What you're seeing here is if you follow the line of water ice at a temperature 60 Kelvin, 60 or 70, you can, even at that temperature, you can retain water ice up to 4.6 billion years, the age of the solar system. If you look at the line of ammonia, which is this one here, at the temperature that MU69 and Pluto are now, you barely keep them over the age of the solar system, which is this line here. If you're looking at the hyper volatiles like CO, methane, and molecular nitrogen, so follow the line of methane here. You see here, already at 40K, you lose them very, very fast. and you would need a temperature of about 20 Kelvin to keep them for about 1 million years, right? So you really need colder temperatures, right? You may think that 40 Kelvin is cold, but you need much colder temperatures to keep these other ices. So formation of MU69 in an optically thick disk keeps the interior cold enough to allow for the volatiles, right, to remain frozen. So if you have drag, then you would have also angular momentum evolution, of course, due to that drag. So you have here the equation of motion. You can put gravity on one side and drag, and solve then for the evolution of angular momentum. And what you find is a very simple system. You find exponential decay of angular momentum, right? So this is what the solution looks like. Angular momentum is here. Then you just exponentially decay that, quite simple. You can do the same analysis here then for the semi-major axis. You see the energy is lost at twice the rate that you lose angular momentum. And then the orbital speed, of course, because you're losing angular momentum, is becoming closer and spinning up. However, just due to drag alone, the time to contact would still be very high, 100 million years, because the Stokes number of these objects, like 10 kilometer size, is still very, very high. You're talking about Stokes number of 10 to the 7. So it would take a long time for it to come into contact. You need something else. So this something else could be first the wind, right? So these objects are not just orbiting in the disk and suffering drag as they orbit. They're also embedded in the subcapillaryan wind of the disk from the pressure gradient. And this wind is usually of speeds of like 50 meters per second. Sounds low, but it's actually very high compared to the orbital speed of these low mass objects, which is about 0.1 meter per second. So the wind is actually 500 times quicker, right? I mean, than the speed that these objects are orbiting each other. So it ought to play a role. So we calculated here the semi-major axis, eccentricity, and angular momentum evolution with the wind. Found here what the analytical solution for these are. Find here that the numerical matches it very well. What you see is that the semi-major axis, decays at a slow rate, but the eccentricity shoots to 1 very rapidly within a time here 1,000 years. So what is going on is that you start from a circular orbit. You nearly conserve angular momentum, which means that your semi-major axis is roughly constant, but you're shrinking the semi-minor axis. So the orbit becomes more and more eccentric. So if you follow this here, so you see here, so it's becoming more eccentric. Eventually, the orbit degenerates into a line, and the bodies plunge into contact, right? So this decay of the semi-minor axis, the increase of eccentricity, is much faster than the decay of energy, the decay of angular, the decay of the semi-major axis. Still, the time scales, when you work them out, turn out that they work for the asteroid belt, but they do not work too well for the Kuiper belt. The reason for that is that the drag is quadratic in the asteroid belt, so that works for that. Once you calculate the drag on one side of the orbit and the other side of the orbit, if they scale quadratically, they do not cancel out. But in the Kuiper belt, the drag is linear, so the wind doesn't really matter that much, because what you gain in one half of the orbit, you're going to lose on the other one. So you can increase the wind here up to 100 meters per second. And as you see here, the influence that is going to have in this region here, which is the Kuiper belt, is not really going to change much. So you still have a time scale that is more than 10 million years. So we need to find something else. So this is an image here that shows here when you pass from linear to quadratic. MU69 is in the region of transition from linear to quadratic, but it's still closer to the linear. What you're seeing here is distance, and here then size of the body. For an object like MU69, which is here, you are roughly at Reynolds here. What is coded here is the drag time. So still about 10 million years. And here then we included the effect of inclination. We changed the inclination of the bodies. And that's when you start seeing more interesting thing happening. I want you to focus on the 60 degrees, which is here, right? So you start from a mutual inclination of 60 degrees, you start to see a cycle happening in the eccentricity and inclination. You increase the inclination, decrease the eccentricity, increase the eccentricity, decrease the inclination. Semi-major axis doesn't really matter much, doesn't participate in these oscillations. These are, of course, Kozai-Lidov oscillations, right? So you conserve here the vertical angular momentum of the orbit, not just the, not the total, but the angular momentum of the binary projected onto the angular momentum of the orbit. And then due to that, you can exchange eccentricity for inclination.
5 minutes.
Thank you. So at 90 degrees, once you start from a very inclined orbit, you see then that the inclination increases, right? And then the eccentricity easily goes to 1. You see here, this red little line means that you reached 1 very, very fast. So we put that in a Kozai-Lidov oscillation code. So in this model here, we're solving the couple. So it's a series of 14 coupled equations. They're solving for the eccentricity vector, which is this equation here, the magnitude of the eccentricity vector, the angular momentum, again, the angular momentum vector and its magnitude, which is this vector, and the spin vectors of the two bodies also. So we solved this series of 14 coupled oscillations, and what you see here is the result. So let me explain here this plot. What you're seeing is on the x-axis is the distance, the semi-major axis of the binary. In units of RB here is the sum of their radii. And then on the top here is that converted to kilometers for the case of MU69. The hill radius of MU69 is here of the order of about 40,000 kilometers, 2,000 times their mutual radii. And these are all of the simulations that we ran here with the Kozai-Lidov code. The field of the solid dots are the simulations where we got contact. Right here on the y-axis, you have the initial inclination. And the empty dots, the hollow dots, are the ones where we did not reach contact. This black line here is the analytical expectation of the critical inclination for contact. So you can see here we follow that quite well. So that's only with Kozai-Lidov. So these are other simulations that we did, including other physics, other physical ingredients. On this one here, the blue dots is the Kozai-Lidov oscillations plus the tides that the bodies induced on each other. As you can see, that ends up not mattering much. The blue line is pretty much, the blue dots are pretty much the same as the green dots. So their mutual tides really don't matter, at least not at these distances that they are. Even here, as you get close, the tides still do not matter. Situation starts to change once you include the quadrupole, the permanent quadrupole. The J2. J2 for these bodies, as they are oblate, is very, very, very high, right? Of the order of 0.1. So contrast that to the J2 of Jupiter, which is of the order of 10 to the minus 6. So what you see here is that there are two things that happen. First, you start having a J2 forbidden zone. So in this region here, you don't have contact anymore. And that's because of the fact that the J2 also leads to precession. So for the Kozai-Lidov oscillation, you need the argument of pericenters to be locked. And precession will, of course, bring them out of this locking, so it kicks them out of the Kozai-Lidov resonance if they get too close to each other. Also, there is a modus increase here in the window of contact beyond the critical inclination for contact, but not by much. Situation changes a lot more when we include drag, which is the red dots here. If you include the drag, you see that you increase the window of contact quite a lot. I was trying to see here if you could avoid having a J2 forbidden zone, but no, the J2 forbidden zone is still there. And what is going on here? Oops. Okay. And what is going on here is what I showed you in the first plot. J2 is leading to a chaotic variation on top of the Kozai-Lidov oscillations. And then once we include the drag, you're decreasing the semi-major axis also, making it easier to achieve contact. That's why you increase that window of contact by so much. So just a last point, I'm just going to mention that even though I'm going on the time because it's important. You can also bring the spin vectors to alignment because the J2 quadrupole goes as the fourth power of the semi-major axis. So it's still very high, about like 5 billion years, and their bodies are distant from each other. But you bring it down to 100 million years once the bodies get very close, about 10 radii. So conclusions, we solved the binary planetesimal problem with gas drag. We implemented the solution into a Kozai plus tidal friction code. We find that the contact is possible in the asteroid belt within a tenth of a million year. The orbits become grazing once you include the J2 and drag. There is enough time for the bodies to come into alignment during the lifetime of the nebula. So we predicted them based on that due to the window of inclinations that about 10% of the Kuiper belt called classical binaries should be contact binaries. And the velocities are also very small, like 3 to 4 meters per second. There are still open questions. How do we combine that with an n-body code? Because there are limitations of using the KozaiLidov approximation. So thank you very much, and I'm going to take questions now.
Thank you very much, Vladimir. So do we have questions? Jake, Simon, please.
Hi, Vlad. Nice talk. So you said in the beginning, this may be just a clarification question. You said in the beginning that gas drag doesn't seem to play a large role, but then later on you mentioned that it does. And I guess I'm just having trouble understanding why it matters when it does. And yeah, when does it matter?
Right. So the reason why it doesn't matter much in the Kuiper belt, or at least that's what one would naively expect at first, is because as you see here, the drag in the Kuiper belt is linear. So what you gain on one side of the orbit in angular momentum, you're going to lose in the other one. So you're down to only have the drag happening in the long time scales of about 10 million years, right? So that's the time scale that the semi-major axis would drop from 1 to 0, right? In dimensionless units. You would need to wait about 10 million years for that to happen. But drag ends up mattering once you have Kozai-Lidov Kozai-Lidov oscillations, because you are not relying on the shrinking of the semi-major axis on a circular orbit. All that you want is the pericenter distance to come into contact, right? So this effect that you are decreasing the semi-major axis, even at a longer time scale, you would take a long time to make this here go from 4,000 kilometers to 30 only, which is what you need for contact. But if you add high eccentricity excursions, eventually during one of these high eccentricity excursions, as the semi-major axis goes down, the bodies can come into contact. So drag alone cannot do it. Kozai-Lidov oscillations alone cannot do it. But if you combine both, yes, you can achieve contact.
Okay, thank you.
Okay, now Chao Chin has also a question.
Hi, Vlad.
Hey, Chao Chin.
Thank you for the talk. I have two quick questions. The first is that what did you assume to find the Reynolds numbers to say that it's linear drag, and and does the viscosity really matter? And the second question is that if you really need Kozai-Lidov oscillation to explain the contact, I would imagine even it's grazing, the collision speed is still very high. And can you explain the low contact speed?
Right. Okay, so the first question, yeah, I used the minimum mass solar nebula here for this plot. So yeah, so these are the drag times on the minimum mass. So that's the densities of the minimum mass, the radii of the body, and I assume the density of about half gram per cubic centimeter, which is what comes from the results of the new horizons, and the typical drag of the nebula. I also tried 10 times the minimum mass, which is shown here in this plot, and the results, you can push it a little further out. So the Kuiper belt distance would be here, right? So if you put 10 times the minimum mass, you bring here this number closer to the quadratic drag, but the drags are still high, are still of the order of like 8 million years or so. I actually had this discussion with Bill McKinnon. Excuse me?
My question was the Reynolds number.
Yes, the Reynolds number is what you're seeing here. No, actually, this is the this is the Reynolds number. So the contour lines here are the Reynolds number. I calculated the Reynolds number directly from the gas properties, the size of the object, and the speed of the wind. All right.
And how about viscosity?
The viscosity also comes from the properties of the nebula.
Alpha viscosity?
The viscosity, yes, comes from the sound speed and the mean free path. Right. So yeah, even if increased to 10 times the minimum mass, you still don't get a time scale here that brings down. I had the discussion with Bill McKinnon. He finds drag times an order of magnitude lower than mine, and we could trace that to several places where there are factor 2s. And usually these factor 2s would cancel out, but in this case, the assumptions he made 3 times, missing a factor 2, you end up with a factor 2 to the third, so factor 8. So that's why he ends up with much lower time scales. The second question is, even if you have contact by Kozai-Lidov, the speeds would be big. That is true if the bodies are spherical bodies, right? If they plunge into contact through a radial line of eccentricity equal to 1, by definition, the speed that they're going to meet is the escape speed, right? Which in the case of MU69 would be about 10 meters per second, which would still lead to a collision that would shatter the bodies. What happens is that these bodies are not spherical. So when they come into contact, the fact that they are oblate makes them meet, we calculated that at 60% of that speed. So that brings down to about 5 meters per second.
But you still have a large tangential velocity, right?
Not much. It's still 5 meters per second or less.
Okay.
Okay, thank you very much, Vladimir. Thank you very much to all. I think that before